Hello Algebra 2. Tonight's topic is for Unit 8, Day 2, so 8.2, and we're graphing exponential, logarithmic, and natural log functions. Our essential question tonight is, can I use my knowledge of A, H, and K to graph exponential and logarithmic functions? Now, on the first day of the unit, you used the iPads and the graphing calculators to take a look at some of these functions, and we're going to come back to these equations in a minute, but these are the same ones that you explored on either Desmos.com or with your graphing calculator. But we didn't really talk about what a logarithmic function is. So first, realize that an exponential function is this example A, B, and C. The logarithmic, they're a little more obvious here. They have the word log in it, or it could be a ln, natural log, logarithmic, and that is the log base E. But they're a logarithmic function. Now the reason we have logs is because John Napier invented them before we had calculators. We didn't have a way to calculate large numbers. So he invented logarithms, which allow long multiplication and division problems to be calculated with addition or subtraction. And by doing this, they were able to save a lot of time, and he essentially doubled the lives of astronomers and other scientists in the pre-calculator era. So it's a great, and they have books of the log, how the log tables were set up, and then the different things we're going to be learning about allow them to solve different problems. Anyways, we'll be talking more about that in the next couple of days, but I wanted you to realize that it was important that these were created. And the second thing to realize is exponentials and logarithmic are inverses of each other. So number A, y equals 10 to the x, is the inverse of our s of x function here, where y equals log 10 of x. So we'll be graphing these shortly, and remember the inverses, when we go to graph using one to the other, we switch the x and the y, and we can find them out algebraically, find the equation, or we could use the table when we go to graph the inverse of the original function by switching the x and y values. The first thing I want you to do is to go ahead and review these 6. It's not all of the ones you had on your paper, but go ahead and look at these 6, the ones I have labeled here, A through F. And I want you to match them to the ones on your graph. Yours are all in black, but they are in the same order as I have here. So go ahead and pause the video, and I want you to label these 6. Use your calculator or use what you filled in from class on the first day of this unit. Okay, when you were comparing the graphs of these functions here, you should have, when you matched them to the graph from your calculator, then you should have noticed that this one is the B equation. So this is the y equals 2 to the x equation. This equation is the D equation. That one is our y equals log base 10 of x. This one here is E. That equation should have matched your log base 10 of x plus 5. This one here is your A equation, y equals 10 to the x power. And this one here is C, the e to the x. And our last one here is F, log base 10 of x plus 2. Alright, I want you to go ahead and pause the video again, and I want you to make some observations here. On the bottom of your page, you're going to make observations about the graphs. The exponential, so remember A, B, and C are exponential, so first take a look at this graph, and this graph, and make some observations about the exponential. Then look at the log graphs, D, E, and F, and make some observation about how what's the same about the logarithmic graphs. And you're going to be writing it in here. So go ahead and pause a minute, make a couple observations, and then come back. Okay, so you should have made similar or maybe some more observations. I just have a few here for each one. And the first thing that I notice about exponential is that they're all exponential growth. They're increasing fast. So if we look at all three of these, the A, B, and C, notice how it's growing at an exponential rate pretty fast here. So these are all growth. And applications for exponential growth, we use a lot of times we hope our money grows exponentially, like in the stock market or in other accounts. Another thing we noticed that it flattens out. Remember from the Desmos activity on the first day when we were talking about where it flattens out. And all three of these, A, B, and C, they flatten out to a horizontal line. And in particular, they all flatten out to the y equals 0 horizontal line. The last thing I noticed is they all have a y-intercept of 0, 1 for exponential. So see how the y-intercept is the same on A, B, and C. Okay, for the logarithmic functions, I noticed that they're also increasing but at a slower rate, and that they flatten out to a vertical line. So the graph for D here, it flattens out to x equals 0. As does E, it's flattening out at x equals 0. And F is flattening out at a vertical line, but it's x equals -2. And we're going to be talking more about, if you notice the three logs, they have the same base, but they moved around a little bit. So we're going to be talking about transformations next. Okay. There is a comparison with the x-intercepts, but because there's some transformations, I did not write that down. We'll be talking about that next. Okay. So first we're going to be using a table to graph our first example here of an exponential function. So we have f of x is equal to 2 to the x. So our y is equal to 2 of the x. And remember, you can input any x value to find your y value. Remember, the input is the domain, or x, and the y is the range. And I'm going to give you a couple of values I want you to try to plug in here, and I want you to see if you can come up with it. So I want you to plug in -2, -1, 0, 1, and 2 as a minimum. You're welcome to plug in more, but go ahead and pause the video, plug those x values into our equation, and find your y values. Okay, so for -2, you plugged it in for the x, so you have y equals 2 to the -2 power. Remember, a negative exponent means you're going to be moving it down, so it's going to be 1 over 2 squared, and you lose the sign then. So 1 over 2 squared would be 4, so our y value is 1 over 4, or 1/4. For our -1, we would have 2 to the -1 power, and that would be equal to 1 over 2, because again the negative exponent moves it down and we lose the sign. For 0, we have y equals 2 to the 0 power. Remember, anything to the 0 power is 1. So our value at 0 for y would be 1. Now these two are probably pretty simple for you. Y equals 2 to the 1 power would be 2. And y equals 2 to the 2 power would be 4. 2 squared is 4. Okay, I want you to go ahead and now plot that on your graph here. Plot these points to see if you can see your equation here. Okay, so in your graph it should look like this, and you should have plotted your points and your exponential growth. For the x-intercept, there wouldn't be one because we're going to have an asymptote here of y equals 0. But we do have a y-intercept, and that it's at 1. And this is a growth, exponential growth, and the whole function will be increasing. If it was decay, then our base would be a number between 0 and 1, and our a value would be greater than 0. So an example of a decay would be y equals 1/2 to the x power, and it would look like this. And remember, decay, an example you've probably seen in science or heard about in science, is talking about half-life. You know, half-life of a radioactive substance is the amount of time it takes for half of the initial amount of the substance to disappear as a result of decay. So that's one you've seen an equation where you've had a base that's a number between 0 and 1 to the x power. Also, another example of a decay, exponential decay, is talking about depreciation of a brand new car. So those, first there's formulas that you can determine how much your car is worth, and the decay is the amount of money that you lose in the first year is a lot. They call that the depreciation value. So we'll be doing more examples with that as well, but wanted to give you some background about decay. The other thing that you need to realize is that our parent graph can be any base. So this is our 2 to the x, and the base here is 2. But remember, for our other examples, we had 10 to the x and e to the x, and they are all parent graphs. So it can be any number to the x power. Transformations occur just like they have with all of our functions with a, h, and k. So notice where a is, h, and k, and remember that a is going to stretch our equation, or it could reflect it horizontally. Also, h is going to move it left and right, and k is going to move it up and down. So we'll be doing more of these in class, but notice the equation of the parent graph and the equation of the transformations. Okay, so remember that the logarithmic function is the inverse of the exponential of the same base. So we can use that knowledge to graph now the logarithmic function. So y equals log base 2 of x is the inverse of y equals 2 to the x. So I went ahead and I think it's all on your same page here, but my table was on a different slide, so it's listed here. I want you to go ahead and pause the video and write in the x and y values for the log. Remember, each x and y switches when you write it in. So go ahead and do that, and then plot your graph. Let's see how it goes. Okay, so you should have switched all your values for x and y, and this is what your graph should look like. Your asymptote is x equals 0. There is not going to be a y-intercept, and notice that there is an x-intercept and it's 1, 0. Also, your function is increasing. Okay, they're going to need a few more minutes to finish these notes, so please click on the link for the second